Okay, folks. So in this video, I will explain to you the uh, nuclear cross section, and there there are a few type of cross sections, but we will focus on the scattering cross section. And by the way, what is the main point? What is the main point of this topic? Is uh, to give you the sense about what is a cross section in a nuclear reaction. So, to begin with, okay, think about an imaginary experiment. Okay? It is called imaginary because uh, this is not what actually uh, perform experiment, but it is rather a thought, okay? uh, a way of thinking on the paper. Okay, so which is why it is called imaginary experiment. Okay, so please so clear up your mind. Okay, and let's think about how this experiment uh, is conducted. Okay, so you think about a tube, a cylindrical tube. Okay, this is the tube, and the cross sectional area of the tube is the size is 1 square centimeter. Okay, so this is 1 square centimeter. Okay, and we are going to experimenting a projectile, okay, uh, an incident particle with a target nucleus. This one is target nucleus. Uh, this one does not move. Okay, only the incident particle is moving towards the target nucleus. Okay, so the incident particle, okay, can be neutron, proton, electron, or gamma ray, or even a nucleus. Okay, and the target usually we refer to a nucleus. Okay, this one does not move, but this one is moving. So sometime I will call this a projectile. Okay, and sometimes I call it with other name. Okay, you may realize that later. So this projectile, this is the target nucleus. Uh, it is written here in the tube there is only one target nucleus or particle. Okay, so the target could also instead of a nucleus, it also could be a particle. Okay, so nuclear interaction may involve a particle and a particle, or particle or a nucleus, or nucleus with a nucleus. Okay, so with that in mind, okay, so this projectile, okay, uh, so the projectile could be particle or ion or nucleus, okay, like I said just now. So it is randomly injected parallel to the tube. So this is the tube. So the projectile is injected parallel to the direction of the tube, or perpendicular to the uh, cross-sectional area of the tube. So if we think if we think what is the likelihood that the projectile uh, will hit either at the side or at the center of the target nucleus, okay, that's uh, physically uh, depend on uh, depend on how depend on how big is the size of the nucleus, the target nucleus. And because we because we declared that the incident projectile randomly injected means that it could be at the top, it could be at the bottom, it could be at the center, it could be anywhere within the cross-sectional area. So uh, so at the end, okay, what influence the likelihood of the collision between the projectile and the target nucleus is the size of the target nucleus. Okay, so the bigger the size, okay, the higher would be the chance of the collision between the projectile and the target nucleus. Okay, so the chance, so point number 4, the chance of collision, okay, collision between the projectile and the target nucleus is proportional to the size of the target nucleus. Okay, so we conclude that the chance, okay, this likelihood of collision is equal to the microscopic cross section, okay, or small sigma. So and that microscopic cross section is the property of the target nucleus, okay, in this imaginary experiment. Okay, instead of the fact that the microscopic cross section just does not only depend on the target nucleus but also depend on the energy of the incident particle and the type of the incident particle. Okay, but in this imaginary experiment, okay, to explain things easier, we consider that this microscopic cross section is the property of the target nucleus. Okay, and the unit, okay, as we said that it is the size that will influence the chance of the collision. So microscopic cross section has the unit of in squared centimeter. Okay, so this was involving a single target nucleus and a single projectile. Okay, so what about if rather than one projectile, okay, we inject a stream of projectiles. Okay, mean that instead of one single projectile, okay, we inject a few projectile, okay, parallel to the cylindrical tube, okay, and we inject them, okay, with constant speed. Okay? So this projectile is with cm per second. This one also v. Okay, so they all have the same speed, same moving speed towards the target nucleus. So mean that in each second, okay, in 1 second interval, okay, the particle travel the particle move uh, v centimeter. Okay, because uh, uh, the speed is v cm per second. Okay, so means that in 1 second, okay, it has moved. The particle has moved v centimeter. Okay, okay, so in 1 second, okay, a column of projectiles in volume v cm plus 1 cm equal to v cubic centimeter is moving. Okay, so so in 1 second, okay, at point number 8, okay, in 1 second the particle move v centimeter. Okay, and at the same instance, okay, a column of projectile with volume v is moving. Okay, because we know the cross the area, okay, the cross sectional area is 1 square centimeter. Okay, and then if you multiply with v centimeter, okay, then uh, you get the volume of projectile move in 1 second. Okay, so in 1 second, they move the distance. Okay, and also uh, in 1 second there is v there is v cubic centimeter of projectiles is moving. Okay, we in the cylinder. And okay, and let's say if somehow you can measure that the density of this moving projectile is n. Okay, it means that there are n projectiles per cubic centimeter. Okay, then what can you conclude is that in a second, in each second, okay, uh, there will be n projectile, okay, moving passing the target. Okay, if we check the unit, okay, if you check the unit, okay, at point number 9, okay, the volume, uh, if you multiply, okay, the speed, oh no, the travel distance in 1 second, okay, with the cross sectional area, which is 1 square centimeter. Okay, you get uh, v in the unit of square centimeter. Okay. Similarly, in point number 10, okay, if you multiply n, okay, the density of the projectiles, okay, so that unit is in projectiles per square centimeter. So this multiplied with the uh, results in point number 9, okay, which is the cubic centimeter. Okay. So you get, because n is projectile per cubic centimeter and v is in cubic centimeter, so those two cancel. Okay. So you end up with uh, your multiplication, which is nv, but in the unit of only projectiles. Okay. So if the projectile is now approaching or just before hitting the target nucleus, okay, after 1 second, okay, uh, we know that there are n v projectiles moving, passing the target. Okay. To put to explain this in different way, okay, NV, okay, NV projectiles per square centimeter time centimeter per second, okay, which is equal to NV projectile per square centimeter per second. Okay, this is called current density. Okay. So uh, NV NV is projectile. Oh, point number 11 is very important, but uh, I'm gonna need a moment, okay, to conclude point number 11. Okay, so uh, from another perspective, NV. Okay. Now I recall. Now I have recalled point number 11. Okay, so if you want to multiply n with v, okay, is uh, n is projectiles per uh, cubic per square centimeter. Okay, this one. So that is n. Okay, and v is centimeter per second. This one origins from point number 7. So you will get uh, so now centimeter is cancelled. Okay. So leave the square centimeter with cubic leave the cubic centimeter with square centimeter. Okay, so you get NV, which is in different unit to point number 10, okay, which is projectiles per square centimeter per second. Okay, and this NV is called current density. Okay, with symbol J. So J is equal to NV. Unit is project times per square centimeter per second. Okay, and J is called current density. So uh, so number 9 in number 10, okay, is just so number 9 is what is what is the volume that moving. Okay? What is the volume of the cylinder that moving in 1 second? That's number 9. Number 10 is uh, the number of projectiles move in 1 second. Okay, in the cylinder. Okay, so in the cylinder, in 1 second, NV is the number of projectiles moving. Okay. Or okay, number 11 is different to number 10. Okay. The meaning is still the same. Okay. The meaning is still the same, but the generality. So the generality of the product of N with V is what we call it the current density. So you might want to pause this video and think about what happened, what is happening in point number 9, number 10, and number 11. But uh, what I can see here, okay, number 11 is the ultimate conclusion that we want to draw in this discussion at this point. Okay, and now we know that current density is J. Okay, now instead of instead of single target nucleus, okay, we distribute the target nucleus evenly inside the cylinder. Okay, and it is known that uh, the density, the spread of the spread of the target nucleus in the cylinder is n. Okay, or the density of the target nucleus is capital N. Okay, just now it's a small n, but this time is capital N. So that's the density of the targets uh, within the cylinder. Okay, so that n, that capital N for the density or the number of, or how many target nucleus per square centimeter, okay, or per unit volume. And small n is how many projectiles per unit volume within the cylinder. Okay, and the cross section or the size of the target nucleus is still the same, sigma. Okay, so now in 1 second, according to point number 10, in 1 second, uh, we know that there are NV projectiles moving passing the targets. So instead of one target nucleus, now we have uh, now we have uh, because one nucleus contribute to sigma. Okay, but now we have uh, capital N nucleus per unit volume. Okay, so now in the unit volume, okay, we have N sigma, total of N, capital N, sigma cross section. Okay. So in 1 second, in the in the unit volume, okay, we have NV. Okay? We have NV projectile that's moving. Okay, and this moving projectile will hit or will interact with the capital N sigma target nucleus. Okay? So uh, this leads to the reaction. Okay, this moving toward this. Okay, the phenomena will lead to reaction, okay, or collision. So in 1 second, okay, in 1 second, in unit volume, okay, the number of passing projectile multiplied with the chance of collision is equal to the multiplication of the projectiles, okay, with the cross with the sum of the cross sectional area. Okay, so that will lead to the reaction. Okay, uh, so this is a bit difficult if you want to try to understand it. Okay, so let's think that the moving projectile, okay, the moving projectile hits the target nucleus, and that uh, that gives us one reaction. Okay, now we have stream of projectile. Okay, and and capital sigma cross section. Okay, so the multiplication of the number of passing projectile in 1 second. Okay, with the chance of collision per unit volume. So it's just the uh, interaction or the reaction. Okay, and since everything occurs in 1 second, okay, so the multiplication of nv with n sigma is uh, what we call it reaction rate. So if you still find that the explanation is difficult, you can pause this video and revisit point number 1 until point number 14. Okay, or you can some text me your question. Okay, for that I can uh, answer you, maybe perhaps using a different way of explanation. Okay, so now knowing the cross section. Okay, cross section of each cross section for each individual target nucleus. Okay, and the density of the target nucleus, the velocity of the projectile, and the density of the projectile, we can calculate our reaction rate. Okay, so our reaction rates. So if you see the equation, okay, so the reaction rate will increase if we have bigger cross section area or higher density of target nucleus, or the higher velocity of the projectile, or higher density of the projectile. I think this clearly make sense. This is clearly makes sense. Okay, because uh, the reaction rates, okay, will increase when you increase everything on the right hand side of this formula. Okay. And there is another way to express R, okay, uh, by putting n b equal to j. We did this in point number 11. Okay, and here, okay, we want to put the capital N, multiplication of capital N with the cross section, okay, with the capital sigma. Okay, this one is sigma, but this is small sigma, this is capital sigma, the uppercase of sigma. Okay, so if you join them together and express them in capital sigma or uppercase sigma, okay, our reaction rate is just the current density multiplied with the uh, uppercase sigma. So what is the unit of for the uppercase sigma? Okay, if you check the unit, R is reaction per second per cubic centimeter. Okay, that is in this bracket. Okay, and current density is projectiles per square centimeter second. Okay, you will get that sigma is the reciprocal of centimeter, okay, or distance. Okay, okay, because reaction and projection does not have doesn't have uh, units, a proper unit. Okay, so you can just neglect them. Second, we cancel, and here power of 2 is cancelled, but this but at the left side uh, you have only the centimeter left. Okay, so clearly the left hand side is centimeter power of -1. Okay, if you move it from the denominator to the numerator, you get the unit reciprocal of centimeter. Okay, and the uppercase sigma is called macroscopic cross section. So macroscopic cross section is the multiplication of the density of the target nucleus with the microscopic cross section. Okay, so this the imaginary experiment number 1 is when we consider that the projectile move uh, in a stream, okay, in an homogeneous stream. Okay, it's continuous with speed v, okay, and in one single direction. Okay, but in real in nuclear reactor, for example, okay, uh, you don't have the situation where the projectile move in a continuous stream. Okay, but rather the projectile move randomly in all direction. Okay, to the right, okay, to the bottom, to the left, upwards. Okay, and 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 possibly in all directions. Okay, randomly in all direction, but at at a constant speed. Okay, let's say it's still we still use the speed v here. Okay, so the speed is the same, but only the direction is random. and and the density is still the small n, okay, per unit volume. Okay, so at an instantaneous time, okay, uh, there are n particles per unit volume, and each of them, okay, moves at the speed of v. Okay, and this time, okay, instead of current density, the multiplication of n with v is called flux. Okay, flux with pi. We use pi. Okay. Pi. No, pi. Pi. Okay. We use pi to express flux. Okay. So the unit is the same with the current density, but only because of current density is stream of particle, okay, in same direction. Okay, we call it current. But now it is not the stream of particle, but rather particle move randomly in all direction. We want it we want to call it a flux. Okay. Physically it's same quantity, okay, but the phenomena is different. So in one direction, in let's say from I want you so we in the in the volume, okay, in not in the volume, okay, okay, in this interacting volume, okay, I want you to think about a surface, okay. Let's say this surface, okay. So this surface is the surface. This surface is in parallel to this to my screen, okay, or parallel to your screen lah, okay. So uh, think about this surface, okay. You can also think the space. Think let's say this is x, y, z direction, okay. So the surface is parallel to the x z direction, okay? And it is perpendicular to the y direction. Okay? So think about this surface. So if you x y z, okay, if you think that, if you consider, okay, the direction that perpendicular to the surface, okay, which is the y direction, okay, according to this Cartesian coordinate, okay. So if you think only the this direction, okay, the negative y direction, okay, then the flux, okay, uh, or not the flux, the current density, okay, because the we said, okay, we said that uh, the current moving only into this direction, only into one direction. Okay, now we can call this, we can call the movement of this projectile as current density. Okay, so that current density is less than the flux, which was nv, and uh, according to the statistic, or more precisely according to the statistical mechanic, the current density will be less than the flux, okay. And on average, if you have nv current flux, then in this one direction, okay, the current density will be nv over 2, okay, half of the total flux, half of the total flux. So this is that is concluded in statistical physics. So we are not doing, we will not discuss that here. Okay, so we use the results. So we use the finding from the statistical physics. So in the y direction, okay, in the y direction, okay, if you consider a unit area, okay, so in one direction, the current density is half of nv. Okay. If you think, so now instead of one direction, if you think the direction from the back, okay, back, this one from the front to backwards, this one backward to the front, okay. If you consider the contribution from both direction, you will get that, you will get the net current density, okay. This one is nv over 2, okay, from the front, and from the back is also the same, nv over 2, okay. So the total projectile that will enter the unit area that we consider here is uh, nv over 2 plus nv over 2. So it is nv. Okay. So even though which is our flux. So even though the movement of the projectiles is in all direction, but if you think the a unit area, okay, a fixed unit area, okay, so the projectile, the the number of projectiles that will enter the unit area is still dn is still mathematically is the product of n with v. Okay. So so the net current density, okay, is the flux. Okay. So why would I consider unit area? So that is to make our argument consistent, because in imaginary experiment one, okay, we consider the unit area, okay, perpendicular to the direction of the stream of projectile. Okay, so even if it is not a stream of particle, okay, you still can bring the similar approach of argument, okay, to make the conclusion. Okay, so here comes the unit area. Okay, so unit area cm square. Okay, so so similarly, you get the reaction rate, which is nv capital N sigma. Okay, now here nv is phi. Okay, nv is phi, so r equal to phi multiply with the macroscopic cross section. So this one does not change here in imaginary experiment. 2 uppercase n multiply with sigma is still the same. Okay, this because the nature of the target nucleus remain the same, but only the incoming projectiles is different. But the final conclusion, or the final formula, is still similar, looks similar. Okay. So okay, so I think that's imaginary. That was the imaginary experiment number 2. Okay. Okay. There are many types of reaction during the collision. Okay. When the projectile hits the target, there are few type of reaction that will occur. But generally, in for this topic, generally there are two. Okay, elastic and inelastic. Okay. So in the elastic collision, okay, or elastic scattering, we call it elastic scattering. The target nucleus, okay, the and the projectile, okay, both will be recoiled. Okay. So changing direction and energy. Okay, that's the elastic scattering. But the in elastic scattering, okay, the projectile will be absorbed. Okay. It will be absorbed into the target nucleus. Okay. Become excited. Okay, and then after that, the projectile is released back again. Okay, so uh, both will move in different direction and different energy. Uh, I will provide another video, okay, in detail to differentiate the elastic scattering and the inelastic scattering. So in elastic scattering, what can I say here is that the energy the kinetic energy will be conserved. Momentum and kinetic energy are conserved. Okay, so the total kinetic energy before the collision and after the collision remain the same. Okay, but in the elastic scattering, the total kinetic energy before collision and after the collision does not conserve, so kinetic energy will be changed. In elastic scattering, so kinetic energy is not conserved. Because part of the kinetic energy is used to excite the target nucleus. And in both scattering, momentum will be conserved like in the collision, like in the collision in mechanics. So if you still remember the collision phenomena in mechanics, in both type scattering, momentum will always be conserved. It's only that the kinetic energy either conserve or not conserve. So that's the conserve is in the case of elastic and the non-conserve in the case of inelastic scattering. Uh, yeah, we say that the reaction with elastic scattering is by the scattering cross section, and the reaction with the inelastic scattering is governed by the absorption cross section, because the projectile is absorbed. So the likelihood that the projectile will be absorbed is uh, expressed using the absorption cross section sigma A. Okay, then this is A, this is S. Okay, for scattering and for absorption. So either type of scattering will contribute to the total cross section. So the total cross section, the the reaction. So the reaction, we don't distinguish why either the reaction is elastic or inelastic. Okay, when you want to calculate the reaction rate, you don't distinguish either it is elastic or inelastic. So you will sum the elastic. You will sum both type of reaction, okay, to come out with the reaction rate. So the total cross section is the sum of the scattering cross section and the absorption cross section. Uh, so we derive few formula. So why don't we use it in example. Okay, so this is for this particular example. Uh, it is in a research nuclear reactor. Okay, research reactor. This is not power reactor. Power reactor has more thermal power output, but research reactor has less thermal power output. And so in this particular example, I bring the typical parameter for research reactor. And by the way, the figure here is the one and only nuclear reactor in Malaysia, located at agency in Malaysia. You can visit the web. Okay, so this is the actual figure or actual image of the reactor at the nuclear at the Malaysian Nuclear Agency. Okay, this is if you try to visual what is inside. Okay, this is what it looks like in the inside of the reactor. Okay, so this particular point that you see is the uranium fuel. Okay, and so typically, so this is not exactly the parameter at the reactor and at the Malaysian nuclear agency, but this is the typical parameter for a research nuclear reactor. And the neutrons, okay, the neutrons, the average neutron in the nuclear reactor move at the speed of 2,200 meter per second. So and that's equivalent to the energy if you at this temperature, okay, and at this neutron energy, okay, the equivalent speed is 2,200 meter per second. Okay, and it is known that the flux, the neutron flux, and at this condition, at the research nuclear reactor condition, is about 2 × 10⁻12 particle per second per square centimeter. Okay, and if you try to calculate the density, okay, in this, I forgot to mention this, in this particular example, it is trying to calculate the density of the neutron. Okay. So as sigma equal to NV, so N is not sigma, phi equal to NV, so N is phi over V. So if you calculate it, okay, be careful with the unit. Okay, you will get that the density of neutron is 10 to the power is about 10 to the power of 6. Okay, or 10 to the 7 lah kan. 10 to the 7 if you get 10, okay, instead of 9. So it's about, roughly it is about 9 times 10 to the 6, okay, per unit volume. Okay, and if you compare this value with the density of water, okay, it is far less. Okay, so the density of this is in order of 22, 10 to the 22, okay, and neutron is in order of 10 to the 6. Okay, so neutron is the density of neutron is uncomparable to density of water. Okay. Even if you compare to the air molecules in the atmosphere, okay, in order of 19, okay, compared to the neutron in the reactor, still in the order of 6. So neutron in the reactor is like, it's like vacuum. Okay. So why I say it vacuum, because the number, okay, their number is overwhelmingly small compared to the number of water. Okay, if you want to compare it water, but even if you want to compare it with air molecule, air that we breathe at this moment, the neutron is far less. Okay, okay, this example will require us to calculate the macroscopic realization, okay, and the reaction rate. Okay, given that the number density of uranium 235, okay, and the density of uranium 235. Okay. So this is the, I think this is typical parameter in the nuclear reactor. I think this is for power reactor, okay, because the neutron flux is higher than the neutron flux in research reactor. So this, I think this is in power reactor. Okay, so if you I hope you can try to perform the calculation by yourself. So what you need is to calculate the macroscopic cross section. Okay, so just now there was a total cross section, which is scattering and absorption, but in this particular example, we neglect the scattering cross section. Okay. So sigma equal to sigma s plus sigma a. So you can neglect the sigma s. Yeah, you see, you only consider the absorption cross section, because most of the time the absorption reaction will lead to fission. So which is why the question asks us to neglect the scattering. Okay, only consider the absorption. So absorption cross section given in this particular situation is given as 681 10 to the minus 24. Okay, so if you do that, you can get sigma sigma is the density of uranium, okay, multiply with its absorption cross section. Okay, and then you want to calculate the reaction rates. Okay, reaction rates, which is flux times the macroscopic cross section. So the flux is given. Okay, so you will get R in unit second minus 1. And by the way, it is purposely written 10 to the minus 24. Okay, so that you can also express the cross section as 681b. Okay, or BAN. Okay, BAN is a special expression to express 10 to the minus 24 square centimeter, okay, for cross section. So 681b. So you can say that the cross section of the uranium-235 is 681 B. Okay? And you may in the future see that people express the cross section using D uh, instead of uh, square centimeter. And next is particle attenuation. Okay. So like in the previous example, we see that we injected stream of particle. Okay. So now we want to see, okay, okay, at the surface of the cylinder, the number of uh, our projectiles are at the maximum. Okay, because here there up to this point there are no target nuclei for the projectile to interact with. Okay, but as the projectile dive further into the cylinder, it will interact. So the far they go, the more reaction uh, they will involve in. And so when they involve in reaction means that they are consumed, so their number will reduce. Okay, so as they go further, their number will be reduced because they are consumed. Okay. uh, so point number one, a stream of particle with similar velocity is directed to the surface of material. Okay, and this particle will be consumed. Okay, because when they are absorbed. Okay, like in uh, this example. Okay, they absorb, so when they absorb, they will be removed from the stream. Okay, so when they collide, they interact, so they are absorbed, so they are consumed, so they will be removed from the stream. Okay, so their number will be reduced. So deeper the stream going into, more particle will be used because of the interaction, and thus the intensity of the stream will be reduced. Okay, so the number of the projectile in the stream will be reduced. So this reduction of part of this reduction of the intensity of the stream is called attenuation. So so the so in so for the conclusion that we will see later, the density, okay, at the zero, okay, before anything happen, okay, it's at the maximum. Okay, and after the distance, it will exponentially reduce. So we will see that later. Okay, so uh, again we are going to derive uh, some some mathematical formula. Okay, so okay, think about very small distance dz, okay, after the surface of the cylinder. Okay, okay, the surface size of the material or the cylinder is for this argument we still consider it 1 square centimeter, and the atomic density, okay, atomic density is capital N. Atomic density is the atom inside the cylinder. Okay, it is not okay, so n is the uppercase N refer to density of the target nucleus. If we refer to our previous imaginary experiments, experiment number 2. Okay. So the uppercase N. So it is still the same uppercase N. Okay. It is the number density of the target nucleus. Okay. So number density of target nucleus is the same. It's the same as the number density of is the same as the atomic density. Okay. And this microscopic cross section of the nuclei is still the small sigma. Okay. So in the material, okay, point number 6, in the material with infinitesimal thickness dz, it is the one dz, the target area, okay, this is the target nucleus. Okay, so the area, if you if you consider the all the area of the target nucleus, okay, within the infinitesimal dz, okay, then the total, the sum of the target area is equal to the atomic density and, okay, the cross section and the thickness. Okay, why would that possible? That is possible because the area, okay, if let me draw the target nucleus at the surface. Okay, dz, that is the thickness dz. Okay, this is the target. The target at the within the dz. Okay, the target nucleus within the dz. Okay. So so the area that will collide with the projectile, the total area is equal to the cross section. If you have one target nucleus, but now you have n, okay, you have n, so n sigma, okay, and dz means that if you have more thickness, means that you have more target nuclei, okay, which is why dz come at the end. Okay, so the unit of n is atoms per square per cubic centimeter. Okay, and the sigma is square centimeter. Okay, and dz is centimeter. But don't forget that the surface, okay, the surface of the cylinder is unit area, okay, which is square centimeter. So if you try to cancel the unit, okay, you will end with okay, atom is unitless, so you can neglect the atom, okay, but at the end, okay, this one will eliminated by this one and this one, okay, so you end up with squared centimeter. Okay, so with this assumption, okay, with the assumption that with the assumption of the surface with 1 square centimeter, the atomic density and microscopic cross section sigma, okay, in within the infinitesimal thickness, okay, the target area that will the physical area that will interact with the projectile is sigma dz. Okay, okay, so that's within the sigma dz. Okay, but if you want to go further, okay, let's say at any point z in the cylinder, okay, And if you if you denote the current density at that particular z as j, okay, okay, perhaps jz. So j is a function. J is the function of z. Okay, moment. In a moment, where's my pen? Okay, if you denote as j, okay, so j is random. J is a random variable. It depends on z. So jz. Uh, so current density. So current density is this is the unit current density, like we discussed previously. So the collision per second, or the reaction rate per second at position z, okay, is the cross section. Okay, the cross section multiply with the current density. Okay, like we did here. Okay, like we did here. That's the current, and that is the area. So this is your current density. This is your area. So in a second, in a unit per second, in 1 second, okay, at any particular position, here or here, okay, anywhere, you can calculate that uh, reaction rate is j uppercase sigma dz. Okay, so which is why, okay, which is why uh, the change of g, the change of j, okay, the change of current density at with distance z is dj equal to minus j uppercase sigma dz. Okay, so let's say let's say let's say this is dz. Okay, so here is j. Okay, here is, let's say, j naught. Okay, because nothing happened. Nothing has occurred here because there's no target nucleus at the surface. But after dz, okay, after dz, now j is reduced by dj, okay, and that magnitude of reduction equal to the reaction rate within the dz. So dj equal to minus j uppercase sigma dz. Why do we put minus? Minus indicate that the reduction of the current density as we go further into the cylinder. Okay, so this is similar. This is similar with the law of radioactive decay. Okay, so with these uh, equations, okay, and if we consider at zero, okay, at zero at the surface, the current density is j naught. Okay, if you integrate dj, okay, you will get j equal to j naught, exponential sigma z. Okay, this is similar like dr to r naught exponential minus lambda t. Okay, so so if you try to plot, okay, you will get reduction of uh, current density with this term. Okay, and in the law of relativity, lambda is the decay constant. Okay, decay constant. Okay. What about sigma? Okay. So in the particle attenuation, okay, in this equation, okay, sigma is sigma is macroscopic cross section. Okay, we know that. Okay, we know sigma is macroscopic cross section with the unit of reciprocal centimeter. Okay, but if you uh, take the risk, if you inverse, if you inverse the sigma, okay, you get sigma. Okay, now the unit is cm. Okay, and we use lambda. Okay, we use lambda to express the reciprocal of sigma. Okay, and if you do this, if we do this, okay, uh, lambda, okay, lambda which is the reciprocal of sigma is called the mean free path. Okay, so this is not the decay constant, but it is called the mean free path. Okay, what is mean free path? Uh, mean free path is the like the name suggests, is it's the average. On average, it is the travel distance of the particle, okay, before it is colliding again, or before it is consumed in the reactions. Okay. So I will read point number one. The particle just after collision, if it's not observed, okay, or will move towards certain direction. So that is target nucleus. That is target nucleus. Okay. So if the particle, okay, if the particle hit now the target nucleus number one, okay, if it is not observed, okay, it will recoil and perhaps move to target number two. Okay, and again after after hitting target number two, if it is not absorbed, it may um, recoil towards target number three. Okay, so 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 from target number one to target number two, and target number two to target number three. Okay, what is the distance? Okay, so on average, the distance is lambda. Okay, so lambda is the, like the name suggests, it is the mean free path. Okay, so it's the path on average, the path that the projectile will take before in between collisions. Okay, so it is lambda, then is lambda on average. Okay, oh, okay, we have example. What is the mean free path of neutron in water? Okay. You will, okay, so given what is the mean free path of one electron volt neutron in water, assume that the nominal process only involve hydrogen. Okay, so if you want to visualize the situation, okay, let's say this is molecule of hydrogen. Excuse me. So if these molecules of hydrogen, okay, we neglect water, we neglect the atom hydrogen, the oxygen atom, only the atom of hydrogens. Okay, so the neutron will only dominantly interact with hydrogen. Okay, so this neutron, it was scattered. So neutron was scattered. Uh, so what is the lambda? Okay, what is the lambda in this case? So sigma, you get to find the sigma. Okay, sigma is sigma s is the n. Okay, and lambda is what? Lambda is reciprocal of okay, sigma. Okay. So you will get that in centimeter. In centimeter, not centimeter square. In centimeter, which is the distance. Okay. So if there is no if at this hydrogen there is no absorption, then the neutron will recoil towards this hydrogen. Okay, and if nothing occur, it will scattered, okay, toward this hydrogen, and so on and so on. So on average, if you try to calculate, I don't remember. I think it's about few. It's less than 1 centimeter, I think. Okay, but that's the average of the movement of neutron in water. Okay, so we will end soon. So this video will end soon. Okay, so as concluding remarks, cm square. Okay, so the cross section, although it is expressed in the unit of area, okay, but it indicate the probability of interaction. So usually sigma is less than 1. Okay, so it is less than 1. So intuitively we know that probability, okay, probability is less than 1. Okay, in probability and statistic, okay, we know that probability is the possible value of probability is less than 1. Okay, uh, that's according to the law of probability, but 0, 1. Okay, bigger than 0 and less than 1, and we know if you try to search by your own self, okay, sigma, the cross section, will always takes value less than 1. Okay, indeed it is very small value, okay, up to the order of 10 to the minus. It can be like the example we use here, okay, in order of 10 to minus 24, and for this one minus 24, sorry, I forgot minus. Okay, so it's in order of minus 24, so it's very small probability. Okay, which is why the density of the of the target nucleus, okay, also contribute to the reaction rate. So cross section is likelihood or probability of interaction. Okay, and mean prefast is just the average. If the projectiles are not absorbed or not consumed, okay, what how does it move in the material? And okay, and particle attenuation, it will decrease exponentially. Okay, indeed it will increase exponentially because of it is consumed in the reactions. And okay, and barn is the unit for cross section. It is just comparison of neutron in the nuclear in the research reactor, and the cross section. Total cross section, we should consider all type of interaction. Okay, doesn't matter if it's stream of projectile or the projectile move randomly in all direction, but at the end the direction rates is the flux time the macroscopic cross section, and for the stream of projectiles, it is the direction rate is the current density multiplied with macroscopic cross section. Okay, so reaction rate increase if you have more projectile, if you move your projectile at high speed. If your target nucleus material of the target nucleus is has high density, or it has the large cross section. So we are not going to discuss in this course how the cross section change with the phenomena. Okay, actually cross section depend on the projectiles. Okay, what is type of projectiles? Okay, depend on the density. It depend on the what is the type of target, and then it depend on the energy of the projectile. Okay, and energy of the projectile for the speed of the projectile. Okay. So all will contribute to the cross section. Okay, which is why cross section, the calculation of cross section is another different big area in nuclear physics. Okay, so that's all for this video. If you have question, please ask me, text me the question, or and I will try to answer that. Okay, so thank you for this. These are the reference that I use. Thank you. Have a good day.